Welcome, everyone. Today, we're diving into the exciting world of message queues with Kafka versus RabbitMQ.
Imagine an e-commerce platform during a flash sale. Order processing grinds to a halt. Payment failures skyrocket. Users abandon carts. Revenue plummets. A synchronous system couples order placement directly with payment processing and inventory updates. High traffic overwhelms the system. Bottlenecks form. Failure cascades. Message queues decouple services. Producers send messages, consumers process them asynchronously. Order placement becomes independent of downstream dependencies, improving resilience. Today, we'll explore two popular message queue systems, Kafka, a distributed streaming platform, and RabbitMQ, a robust message broker. We'll dive into their architectures and key differences. Let's start with Kafka. It's designed for high-throughput, fault-tolerant, real-time data feeds. Its core strength lies in treating data as a continuous stream. But what about durability? If a broker fails, is your data lost? This is where Kafka's architecture shines. It uses topics divided into partitions which are replicated across brokers for fault tolerance. Now imagine 10,000 orders per second hitting your system. How do you keep up? Producers write messages to partitions, and consumer groups read from them in parallel, enabling massive throughput. But with all this parallelism, how does Kafka handle ordering? It guarantees message ordering within a single partition. Consumers track their progress with an offset so they can resume processing. Now, let's switch to RabbitMQ. It's a versatile message broker that excels in flexible routing and complex messaging patterns, implementing the AMQP protocol. So how does RabbitMQ actually route a message? It's a four-step dance. Producers send messages to exchanges, which then intelligently route them to one or more queues based on rules called bindings. This routing power comes from its different exchange types: direct for one-to-one, topic for pattern-based routing, and fan-out for broadcasting messages to every subscribed queue. But what happens if a consumer crashes mid-process? This is where acknowledgments are critical. A consumer signals completion only after processing, telling RabbitMQ it's safe to delete the message. Comparing them directly, Kafka is stream-oriented. It excels in high-volume, ordered event streaming and log aggregation, acting like a distributed, persistent commit log. RabbitMQ is a traditional message broker. It's ideal for distributing tasks among workers, complex routing, and inter-service communication in a microservices architecture. Let's discuss delivery guarantees. At least once delivery means a message is guaranteed to arrive, but network issues could cause duplicates. This is why consumers must be idempotent. Processing a duplicate message, like updating an order status, should have the same result as processing it once. Exactly once delivery guarantees each message is processed precisely one time. This is the holy grail, but it's complex, often requiring distributed transactions and higher overhead. Kafka offers at least once by default. Achieving exactly once semantics requires careful configuration, like transactional producers and idempotent consumers, or using Kafka streams. RabbitMQ provides at least once delivery with publisher confirms and consumer acknowledgments. Exactly once is generally not a built-in feature and requires careful application-level implementation. Message persistence is crucial. Both Kafka and RabbitMQ persist messages to disk, ensuring they survive broker restarts. Kafka's append-only log and replication are key here. So how do they scale? Kafka scales horizontally by adding more brokers and partitions, making it a beast at raw throughput for large-scale, sequential data processing. But what if you need complex logic, not just raw speed? RabbitMQ also scales horizontally, but its strength is in managing intricate routing and distributing work to many small consumers. Monitoring is vital for both. For Kafka, you'll use tools like Prometheus to track consumer lag, broker health, and throughput, often visualized with Grafana. And for RabbitMQ, what should you watch? Key metrics include queue depth, message rates, and consumer connections. Unhacked messages can be a sign of slow or stuck consumers. For reliability, consider circuit breakers on consumers to prevent cascading failures if a downstream service becomes unresponsive. Dead letter queues capture failed messages for later analysis and reprocessing. Specifically, if an inventory service fails to process an order message, the dead letter queue holds it. This allows for retry mechanisms or manual intervention without data loss. Choosing between Kafka and RabbitMQ depends on your use case. Kafka for high-throughput event streaming and log aggregation, RabbitMQ for flexible routing, task queues, and microservice communication. But it's not always an either/or choice. In fact, many production systems use both, Kafka as the event backbone for analytics and logs, and RabbitMQ for specific transactional task queues like sending an email. They are complementary, not mutually exclusive. So what's the one key takeaway? Think of it like this. Kafka is for replaying events, RabbitMQ is for delivering tasks. One is a tape recorder, the other is a post office. Your choice depends on what you need to do with the message after it's been sent. If you're starting out, RabbitMQ's simplicity is a great choice. When you need event sourcing or millions of messages per second, it's time to graduate to Kafka. Remember, both add operational overhead, so ensure the benefits justify the cost. Thank you for watching.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.